Hello, this is Brian Washburn. I'd like to talk about the frequency of small oscillations. So let's consider this problem. Say I have a potential energy U of R, and here I'm plotting UR as a function of position. Okay, and this particular potential has a equilibrium position. I can determine that by taking the derivative. Remember that minus the derivative potential equals the force. So this place the force is equal to 0. But notice also that that equilibrium position is a stable equilibrium. That means that if I get displaced about U of R a little bit, the force will cause it. It was a restoring force, it causes the force back. Okay. Now, say what I want to do is I want to describe a particle that experiences this potential energy. How would I solve for its motion? Well, in general, what I need to do is from the potential, calculate the force, and then take the force and put it into F equals ma and solve the equation of motion. Now, this is a fairly complicated potential, thus the force is fairly complicated, and it may be in a form that I can't solve analytically. However, what I may be interested in is motion not at any value r, but motion about the equilibrium point. Okay, so if I want to look for small oscillations about this point, and since this is a stable equilibrium point, if I displace it from here, I expect it to oscillate at some frequency, some natural frequency, and that is the frequency of small oscillations. So how do I solve that? Well, one way you may think, well, let's just take this function here and Taylor expand U of R at R equal R naught. And I wanted to get it look like simple harmonic motion. The potential energy for simple harmonic motion is quadratic, so it looks like 1/2 kx squared, or in this case 1/2 kr squared. Okay, so I could Taylor expand this and keep the second order term. But when I do that, I'm only going to get something. I'm going to get k. I'll get the linear. I'll get a restoring force. I won't necessarily get the frequency small oscillation. Okay, and again, when I Taylor expand it, I'm going to set r equal to r naught plus delta, where delta is something small. Specifically, delta divided by r naught is much less than 1. Now, the way we're actually going to do it is I kind of have steps. So instead of looking at the potential, we're going to actually look at the force. Okay, and so this is kind of my method. Again, I want to calculate omega naught, the frequency of oscillations about an equilibrium point. Okay, what is my method? First thing I'm going to do is determine, I know what the force is, a function of r. I'm going to find the equation of motion. I'm basically going to say x double dot. Now this could be r double dot, but whatever variable you're using, I'm going to find the equation of motion. X equals F over m. Second step, I find the equilibrium positions. All right. Now, before you just take an arbitrary force, you should look at that force first and figure out if it has any equilibrium positions, because if it doesn't, then none of this will work. And that's where plotting functions, potential energy curves are essential. So we're going to assume that it has a stable equilibrium point. Okay. Now I've actually find the value in step 2 of the equilibrium position. I set x equal x naught, and thus x dot equals 0, x double dot equals 0. I stick that into the equations of motion here. Okay. Now in the end, what's going to happen is that's static equilibrium. Okay. And so that's going to allow me to solve for x naught in terms of my given variables. Okay, now step 3. What I'm going to do is set x equal to x naught plus delta, where delta is something small. Then I'm going to take derivatives of x. So x dot, now since I'm going to take a derivative of this thing here, okay, well, this is a constant, so then x dot is equal to delta dot, and x double dot equals to delta double dot. I stick all that stuff into my equation of motion here, okay, and I'm going to get something of the form that kind of looks like this: delta double dot plus some constants times delta plus some set of constants equals 0. Now when I do that, I may need to, well, most likely I will have to do some Taylor expansion. When I Taylor expand things, I'm going to keep terms up to delta only, okay, and so this is what I'm going to get. Now, what's going to happen is this term here, this second term, this term here is going to be equal to 0 from the equations I get in step 2. All right, you may not believe me, but I'll show you an example in a minute. What does that leave? That leaves just this equation here, okay? And that equation there is simple harmonic motion. Okay, so it's x double dot is plus some constant times delta equals 0. Well, that stuff and that constant is omega naught squared. So what we've done is really we've taken our force, Taylor expanded it to look like Hooke's law and write down simple harmonic motion, and thus I can describe the frequency of oscillation about that equilibrium point. That's the method. So let's take a look at an example. Now we'll do this in class, but one thing that people have troubles with in doing this is the Taylor expansion part. Okay, so I think the more practice, the better. I have some force that looks like this. And by the way, if I give you a force, you should always be able to calculate the potential energy associated with that, okay, and plot that potential energy. And so, just because I give you a force, you should prove that, hey, does this thing have a stable equilibrium point? That's the important thing. Okay, it does. All right. Now what do I do? Step one. Step one, what I'm going to do is I'm going to find equation of motion. Okay, mass, that's pretty easy. Mass times acceleration equals to the net force. Okay, there's only one force acting on it. Step two, I want to find the equilibrium positions. All right. So I said R equal R naught, R dot equals 0, R double dot equals 0. This gives me, this is static equilibrium. And now I can solve for R naught. So I'm going to take this stuff, put it on that side. R naught is going to be equal to the fourth root of K over B, or beta. So that's a constant. Okay, that's just a constant. And again, K and beta are both positive numbers. Let's just say that. Step three, this is the hard step. I'm going to set R equal to R naught plus delta. R dot equals delta dot. R double dot equals delta double dot. Stick that into this equation of motion here. And then I get this stuff here. All right, now, this is where people get in trouble. How do you Taylor expand? Remember, when I Taylor expand, I have to define things small. Now, delta, you may say, well, delta is small. But really what's small is delta over R naught. So what I'm going to do is factor out an R naught. And then if I take R naught, so this term here, I'm going to Taylor expand. This term here, well, I'm not going to Taylor expand because it's just a polynomial. I'm just going to multiply it out. Okay. Okay, now what I do is I factor R naught, so I get R naught squared, and I get 1 plus delta divided by R naught. This term here is small compared to 1. Then I'm good to go to Taylor expand. For the other term, I just multiply this out, and I get all this stuff here times the minus sign. Okay, now what do I do? Okay, now I Taylor expand. Do that here. Sorry. So now I have an expression 1 plus something small is approximately equal to, now I know this Taylor expansion, and sometimes we just kind of know Taylor expansions. You can do this, you can derive this yourself, it's pretty easy. I think you did a homework problem, I don't remember. But basically this is approximately equal to 1 minus 2 times this ratio here. And there's higher order terms. Again, ignore the higher order terms because they're going to be of delta squared. I take this expression and stick it back and I put it into here. Okay. And then here I have the expanding out the quadratic I had before. I'm going to ignore this term here because it's of order delta squared. And then what I'm going to do is I'm going to group terms. Constant term, okay, things as a constant, and then stuff times delta. And you can bring it all on one side. And then let's take a look what I get. I get delta double dot equals to this thing is a constant, okay. Everything is in a bracket times a constant 1. Then everything in this bracket times this. Now take a look at this. Notice I only have R naughts into there. Okay. Well, this equation is equal to this. All this stuff is equal to 0. Why? Well, because of what we had before. So in step 2, when we set R equal to R naught, we got this equation. That's the same equation that's in the brackets. Thus, I can set the stuff in the brackets equal to 0. Okay, so then all this stuff is equal to 0 because of that term. That leaves this stuff here. So now, notice that this is 0, so I got this plus this times that. All this stuff here is the natural frequency. So I get a differential equation that looks like that, where this is equal to all this stuff here. Now you may say, well, wait a minute, I got R naughts in there. Shouldn't omega naught really not depend on R naught? Well, what you could do is you could take the next step. Instead of putting R naught, you substitute the value from R naught and get the natural frequency all in the parameters of the system. And the parameters of the system are K, M, and B, or beta. So that's it. So that's an example. We're going to be doing this multiple times throughout the entire class. And again, when we talk about simple harmonic motion, I remember said the power of simple harmonic motion is that, in nature we're gonna see very complicated potentials, but under certain conditions they only oscillate very smallly. That's a great word. And yeah, they have very small oscillations. So then what we can do is we can use what we learned about simple harmonic motion and get that frequency of oscillation. And that's important in many areas of physics. All right, take care. Bye-bye.